Good morning everyone. Now I am going to discuss a problem on verification of the Green's theorem. Okay. In that, the given integral over C mdx plus ndy, which the simple closed curve is bounded in the region capital R, and that bounded region is in rectangular form. In that case, how we can find out the verify of the Green's theorem? Okay. Now I am writing the problem and how we can find out the verification of the Green's theorem. Verify Green's theorem. Verify Green's theorem for f bar equal to x square plus y square into I minus 2yxj taken around the rectangle, taken around the rectangle. Bounded by the lines, bounded by the lines x equal to 0, x equal to a, y equal to 0, y equal to b. Here the given function is in vector form, which is in vector form means the function is in a round shape. That round shape is bounded by a closed region which is in xy plane. That shape is in a rectangle form. That is nothing but, if rough diagram, suppose it is a curve C, it is bounded by the closed region which is in the rectangle form, means that is the limits are from 0 comma 0 and a comma 0. This is a comma b and it is 0 comma b. That is nothing but, here we are taking, this is the xy plane. In that the bounded region, the curve over C is a rounded curve, is bounded by the rectangle region. Those limits are from 0 to a and 0 to b. That is nothing but x and y. Limits are 0 to a and 0 to b. In the rounded curve, simple closed curve is bounded in the rectangular region, means here curve C is equal to C1, it is C2, it is C3, it is C4. That is nothing but, simply we are taking the closed region which is in the bounded shape, that is 0 comma 0, it is a comma 0, it is a comma b, this is 0 comma b. Here it is C1, this is the C2 curve, it is C4 curve, it is C3 curve, it is C4 curve. Okay. In this, the line integral for the verification of Green's theorem means integral over C by Green's theorem means, by Green's theorem, the theorem is integral over C mdx plus ndy is equal to bounded with the region that is in xy plane, that is dou n by dou x minus dou m by dou y into dx dy. Okay. Here in the double integral, directly we can take the limits of x and y are from 0 to a and 0 to b. Okay. In region capital R, we can take x limits from 0 to 1, 0 to a, y limits from 0 to b. Okay, it is in xy plane. This is in double integral. In curve, simple closed curve C, in this case, the over curve C is divided into 4 curves, that is integral over C1, integral over C2, integral over C3, integral over C4. The sum of the line integrals of 4 curves is equal to the makes a simple closed curve. Okay. In this case, along with the C1, the x limits from 0 to a. Here y is a constant, means y is equal to 0. From this, dy is also equal to 0. Derivative of that variable is 0. In the C2 case, the constant value is x equal to a. From this, dx equal to 0. Y limits from 0 to b. That is in C2. In C3, the b is a constant. So, in the C3, y equal to b. Then dy is equal to 0. X limits from a to 0. In C4, x variable values are equal. So, x equal to 0. From this, dx equal to 0. Y limits from b to 0. If we have the idea about the line integral, that line integral of simple closed curve is divided into how many curves? If in a rectangle the 4 sides are there, the simple closed curve is divided into 4 curves. One is C1, one is C2, one is C3, another one is C4. Okay. In that, which is the constant value is there, then we can take that value and derivative of that function, which is varies from one value to another value. We can take that variable's integral value, that is 0 to a in C1, 0 to b in C2, y variable in C3, a to 0 in C4, b to 0. Okay. When we have this idea about the line integral and in a double integral of region capital R, then we can easy to verify the Green's theorem. Okay. From these clues, and here what is given? Given circular function f bar is equal to x square plus y square into I minus 2yxj. We know that in the circular motion, in the circle C, integral over C, f bar dot dr bar is equal to integral over C m dx plus n dy. Here given f bar is this one, dr bar means position vectors derivative, that is dxi plus dyj. Find out f bar dot dr bar is equal to x square plus y square into I minus 2yxj. In between of two vectors, we can take dot product dxi plus dyj. Then it is equal to x square plus y square into dx minus 2yx dy, which is equal to mdx plus ndy. Okay. Here what is m and what is n? Here m is equal to x square plus y square, n equal to minus 2yx. These two are differentiating with respect to, first m is differentiating with respect to y. It's 0 plus 2y. Then dou m by dou y is equal to 2y. Dou n by dou x is equal to, it is minus 2y into 1. Then dou n by dou x is equal to minus 2y. By using Green's theorem, we can find out difference of dou n by dou x minus dou m by dou y. It is equal to minus 2y minus 4y. From the RHS of in Green's theorem, RHS value is integral over r dou n by dou x minus dou m by dou y into dx dy. It is equal to x limits from 0 to a, y limits from 0 to b. Dou n by dou x minus dou m by dou y is minus 4y into dy dx. It is equal to integral over the limits x from 0 to a minus 4y integration is 4y square by 2 limits from 0 to b into dx. 2 1s are 2 2s are. This is equal to integral x from 0 to a minus 2 y square limits from 0 to b dx. Limits integral x from 0 to a, this is minus 2b square minus 0 into dx. This is equal to minus integral x from 0 to a minus 2b square into dx. It is a constant. Then integration is x 1 dx. Integration is x from 0 to a, that is minus 2b square into a minus 0, that is equal to minus 2a b square. The RHS value in the region is, in the region capital R, RHS of Green's theorem is minus 2a b square. Okay. In LHS, the LHS of Green's theorem, integral over c m dx plus n dy is equal to, divided into 4 curves, integral over c1 m dx plus n dy plus integral over c2 m dx plus n dy plus integral over c3 m dx plus n dy plus integral over c4 m dx plus n dy. Here m is equal to x square plus y square, n is equal to minus 2yx. In curve C1, x limits from 0 to a and y is 0. Y is 0 means differentiating that y variable dy is equal to 0. Therefore, integral over c1 m dx plus n dy is equal to integral over c1 x square plus y square into dx minus 2yx dy. These values substitute in the curve C1, then it is equal to x limits from 0 to a x square, y value is 0 into dx minus 2 into 0 into x into 0, then it is equal to integral x from 0 to a x square dx. The integration of x square is x cube by 3, limits from 0 to a, that is a cube by 3 minus 0, it is equal to a cube by 3. This curve C1. In curve C2, the constant variable is x equal to a, it is a constant, then dx equal to 0, y varies from 0 to b. Then these values substitute in integral over c2 m dx plus n dy, it is equal to integral over c2 x square plus y square into dx minus 2yx dy. Here x equal to a, this is equal to integral y limits from 0 to b. And in the place of x substitute a square plus y square into dx is 0 minus 2ya into dy. It is 0, then this is equal to integral y limits from 0 to b minus 2ay dy. That's integration is integral over c2 m dx plus n dy is equal to minus 2a, y integration is y square by 2, limits from 0 to b, which is equal to minus 2a b square by 2 minus 0. 2 get cancelled. It is equal to minus ab square. Next, in curve C3, y is equal to b is a constant, then dy is equal to 0, x limits from a to 0. Then integral over c3 m dx plus n dy is equal to integral over c3 x square plus y square into dx minus 2yx dy. Substitute y equal to b, dy equal to 0. dy equal to 0 means it will become 0. Is equal to limits x from a to 0, x square plus b square into dx. It is equal to x square integration is x cube by 3 plus b square into x, limits from a to 0. It is equal to a cube by 3 minus plus ab square. Upper limit is 0 minus a cube by 3 plus b square a. It is equal to minus a cube by 3 minus ab square. It is curve C3. In curve C4, y is equal to, y varies from b to 0 and x is a constant, that x is equal to 0. in C4. So dx also equal to 0. Integral over C4 m dx plus m dy is equal to integral over C4 x square plus y square into dx minus 2yx dy. Then integral over C4 m dx plus m dy equal to integral C4 0 plus x is 0 and dx is also 0. X is 0 and dx is 0 minus 2y into 0 into dy. It is 0. So integral over C4 m dx plus m dy is equal to 0. So here substitute all the curve integral values. Integral over C m dx plus n dy is equal to, the first integral over C1 is a cube by 3. In C2 the value is minus a b square. In C3 minus a cube by 3 minus a b square plus 0. Minus a cube by 3 plus a cube by 3 get cancelled, is equal to minus 2ab square. That is the LHS value. Therefore, RHS is equal to minus a 2a b square is equal to LHS. That is, therefore, integral over C m dx plus n dy is equal to double integral over R dou ny dou x minus dou my dou y into dx dy. Therefore, Green's theorem is verified. Green's theorem is verified. It is the procedure of verification of Green's theorem. Okay, thank you.